All right. So, hello everyone. So, if you're wondering why I am in this get up right now, I actually just attended an event in my elementary school. It was the foundation event, and I was a guest there, and that was pretty fun to say the least. So, aside from that, now we are again dealing with a discussion in integral calculus uh, regarding the integration techniques that we should be utilizing when evaluating various forms of integrals. All right. So actually, we have four major integration techniques that we utilize mostly for the rest of the semester in integral calculus, and that would be U substitution, trig substitution, integration by parts, and partial fractions. So actually, we are very familiar already with the U substitution since we are using that. We have been using that since the first weeks of the semester, and the other three we would be discussing are in the later weeks of integral calculus. And it would be nice if we had a background, if we had an overview of those said topics, namely Trig-Sub, integration by parts, and partial fractions. And before that, since this is basically technically an ambitious video, since we'll take kind of long, especially dealing with those tedious techniques, I would like to give some shout outs. So, firstly, I would like to give a shout out to ME1203. That's my block in college in my mechanical engineering course program. And yeah, love you guys. That's all I can pretty much say. And also, I have some. I also want to give some shout outs to my friends in the other blocks, namely Rowell. He's my cousin in ME1201, and my friend Jed Robin from ME1202. Furthermore, I would also like to give some shout outs to our professors in integral calculus, namely Dr. Emil C. Alcantara and Dr. Renson A. Robles. Also, before we start, I just want to give another special shout out to my cousin, Kuya Jake. He actually just left like 2 days ago for abroad, where he would be working there for around 2 years. So yeah, I'll miss him a lot. And also subscribe to Black Pen Red Pen. I actually got these examples from here, and I would be putting the link uh, in the description for his video regarding this. And we are completing his video by also answering the examples he had put and explaining how the techniques worked. And before we move on, I just got this simple quote: differentiation is merely a skill, integration is an art. And we will see later on how it really differs from taking the derivative of a function. All right. So without further ado, let's move to the first example. And actually, I got some notes here in case I forget some of the concepts discussed here, since I did this a few days ago, and maybe I would have maybe not. I hope so, that I have a few gaps in my knowledge. All right. So first one, we have the integral of ln x over x cubed dx. So looking at it from first glance, we know that u substitution will not work on this function, since neither of the derivatives of the numerator and denominator is on the function itself, right? So what technique are we going to use? That's right, integration by parts. So we will use the DI method to integrate this function, and I actually have a video on that, explaining what it is, when we should stop, integrating and differentiating all that stuff. You can check that out. I'll also put the link in the description below, and you can also check out other sources regarding that. Okay, so to do the DI method, we have to choose a parameter that we are going to differentiate and one that we are going to integrate. All right, all right. So you have a d and the I, and also don't forget the plus minus, since that's a concept of the uv minus the integral of b du, the integration by parts. This makes it easier. Okay, so we will differentiate ln x. All right, and we will integrate 1 over, actually no, x cubed, right? 1 over x cubed, yeah, 1 over x cubed, since we just took out the constant 1 from that. Okay, the derivative of ln x is 1 over x. And if you look at this from this form, this is the same as x to the negative 3 power. And we can just apply the power formula for that, and we will have 1/2, right? Yes, 1/2 of x minus 2, x to the negative 2 power. And this is negative as well, and to make this positive, we can bring this down to the denominator. So the integral of x to the negative 3rd power is negative 1 over 2 x squared. X squared is on the bottom. Okay, and the first part of our answer actually is the product of these two. Okay, we have to multiply that. Okay, so let's do that real quick. So I have negative 1 over 2 x squared. Okay, then the ln x minus, okay, minus the product, the integral of the product of this row. So we have to multiply it first and then get the integral of this, right? You have to get the integral of that. So when we multiply 1 over x to negative 1/2 x squared, we're just adding another power to the bottom. So that's the integral of negative 1/2, right? X to the 3rd power dx. Okay, let's see if I'm doing it well so far. Okay, now what we can do actually is copy the first part of the answer, 1/2 x squared ln x minus, we can take out the constant 1/2 from that. Yeah, 1/2, right? And it's positive since we evaluated this part already, and it's just standard minus over there. And we have the integral of x to the negative 3 power dx, and we know that this is the answer to that. So let's just put it in here real quick. Negative 1/2 x squared. Actually, yeah, it's 1/2. Negative 1/2. Apologies for that. Okay, it's negative 1/2 right there. I was confused by this. So when we distribute negative 1/2 to this, we're just simply multiplying the power and making it positive, and then we distribute the negative sign afterwards. Okay, so our final answer would actually be negative 1/2 x squared ln x, okay, minus, yeah, that's a minus 1/4 x squared, yeah, x squared, and then we put plus c. We're actually done. This is the final answer. So that's how you perform integration by parts. And there are actually multiple steps to this. I won't go further into detail. Yeah, since there are 3 stops, and you can figure that out when we arrive at that on our discussion. Okay, moving on. Now we have the integral of secant to the 4th power x dx. Okay? To evaluate this integral, we have to rewrite it. Let's say I have the integral. Let's rewrite this as of the form secant squared x times secant squared x. And we know that secant squared x is the same as tangent squared x plus 1. Okay, let's put a dx here. Okay, so we have the integral of secant squared x times tangent squared x plus 1. And now you might be thinking we distribute secant squared x, but actually no, we can do a u substitution here. Okay, so we can let our u to be tangent x, right? And the derivative of tangent x is secant squared x dx, which is pretty nice since we have that on this integral. Okay, so we're just basically integrating this in the u world. Okay, so we have the integral of tangent squared x is the same as u squared plus 1 du. The integral of u squared in the u world is 1/3 of u, which is tangent x, and then this we add another power here, so that becomes cube, the tangent x, tangent to the 3rd power x, plus the integral of 1 in the u world is u, and u is tangent x, and we put a plus c. We're done. Okay, that's pretty nice, isn't it? So that's the concept of u substitution. Okay, we simplified a little bit and we applied u substitution. Okay, now for this one, all right, we can try completing the square on this one. We have tackled that, but it's going to be kind of tedious since the numerator is not really to our liking. So this is another concept that we can use in evaluating integrals, and that is partial fractions. So we notice that this whole denominator is something that we can factor out, and we can factor that out in our heads. So we have to think of a number that adds up to 5 but multiplies to 4, and that's just 4 and 1. Okay, so we can think of this as x minus 1 times x minus 4, and you can fold that and you will get this answer. All right, that's pretty good. Now, okay, now this is where the kind of tricky part comes in, since we factored out these, what do you call this, these, and we factored out a new denominator, then we will have to change the denominator as well. Okay, all right, so now what we can actually do here, we can rewrite this of the form the integral of, we can look at this as of the form the integral of 2x plus 3 over x minus 1 plus, I think, yeah, and we copy the same thing here, x minus 4, kind of like that, the x. Is it like that? Yeah, I think so. Okay, now we will utilize that, and we will put x minus 1 here plus x minus 4 here. And actually, we don't use these numerators, okay? Since we are performing partial fraction decomposition. So there's a definition for that, but we will do an easier method. Let's denote this, let's say A, and this is B, the x. Okay? And when I say it's going to be easy, it's pretty straightforward, and this is what we call the cover up method. Okay, so how this works is, if we want to compute for, let's say, this variable right here, we will cover up its denominator. And now you would like to ask yourself, what number would make x minus 1 0? And actually, what makes this fraction undefined? So since our denominator is x minus 1, the value of 1 will make it 0, and it will be undefined since we can't divide by 0. And now, since we covered that up, we can substitute these values over here. Okay, we can substitute that values over here, and actually we're going to use this part of the equation right here to solve for A. So that's basically a simple way of how I can explain the cover up method for partial fractions, since we will be using this a lot in the later topics. So when we plug in 1, okay, let's say this is 1 and this is 1. 2 times 1 is 2, plus 3 is 5, and then 1 minus 4 is negative 3. So our A is equal to negative 5/3. Okay, and computing for B, we cover this up and we ask ourselves, what makes this fraction undefined? That is when x is equal to 4, since 4 minus 4 is 0, and it will be undefined. So now we use this part of the equation right here. Okay, now we put 4 here and 4 here. 2 times 4 is 8, plus 3 is 11. Where should we put it? Let's put it right here. 11. And 4 minus 1 is 3. So B is 11/3. Okay, I think that's how it works. Okay, so we actually now have the integral of negative 5/3 over x minus 1 plus let's just keep it in one integral, plus 11/3 over x minus 4 dx. Right. Okay, and now we can just take the constants out and we can perform u substitution. Yeah, since we can take this out of the integral, all that good stuff, and then it will be 1 over x minus 1. That will give you an ln function if you do the u sub. So you can do that in your head, and I'll just go straight to the final answer. So if you perform u sub here, you should get an answer of negative 5/3, right? Ln of the absolute value of x minus 1, okay, plus 11/3 ln of x minus 4. and then we can put plus c. And if you want the answer to be like in one fraction or something, then you can just combine it into one fraction right here. Okay, since this will be the negative fraction of 5 ln of x minus 1 plus 11 the 11 ln of, okay, ln of the absolute value of x minus 4, and then this is all over 3, and we put plus c, and we are done. This is the final answer. So that is one of the basic concepts of how partial fractions work. The way I did it is like a simplified partial fraction decomposition by the means of the cover up method. Okay, all right, and now we can move on. Now for this one, we have the integral of x squared tangent x cubed dx. Yeah, and for this one, we can just do a simple u substitution. Okay, since u is equal to x cubed and du is 3x squared dx, and since we have an x squared there, we can multiply both sides by 1/3, so 1/3 du would be equal to x squared dx, since the 3 will cancel over on this side. Okay, all right. So now we have 1/3 of the integral of tangent of u du. Okay, and we can do this legitimately, but the integral of tangent u is just the ln cosine of u, right? The negative ln, yeah, negative ln cosine. Since if we set this to be cosine over sine, then we let u to be sine, yeah, and yeah, if we let this is actually a new substitution here. Yeah, let's say we do a w sub, and if you choose your w to be cosine, since this is the same as sine over cosine, and the derivative of this is negative sine, and you can go from there to evaluate the integral. So yeah, by definition, the integral of tangent, let's just go straight to the final answer. The integral of tangent u is the negative ln, so I put a negative here, and then the ln of cosine, and our x is x cubed, and our u actually, rather, apologies, is x cubed. Put plus c, we're done. Let's put a parenthesis actually here though, so we can distinguish from it. Okay, we're done. Okay, moving on. Number 5. Now this is a even trickier integral. So we have the integral of 1 over the quantity 1 plus x squared raised to 5 halves dx. Okay, now what have we noticed with this with this equation, right? Okay, right. So if you go back to number 2, where's that? We know that secant squared x is the same as tangent squared x plus 1. Now, if you look at this and ask yourself, wouldn't it be nice if that x squared was tangent? And then we can we can like derive a secant squared from that, and then we can go from there. That's right. This is trig substitution. Okay, let me show you. Let us suppose that our x is equal to tangent theta. This theta will be important later on. Okay, and yeah. And the derivative and dx is secant squared secant squared theta d theta. Okay, and actually look at here, this is going to be pretty nice. Since we did the trig substitution, now we have the integral of 1 plus x is tangent. Okay, so we have tangent squared theta on the denominator. We have 1 here, and don't make a mistake here, dx is secant squared theta d theta, and then this goes on to the numerator. Let's just put it here right now. So secant squared theta on the denominator, and we raise this to 5/2. Don't forget 5/2. Okay, we really just erase that, but we have now the integral of secant squared theta over 1 plus tangent squared theta is the same as secant squared theta. Secant squared theta raised to 5/2 d theta. Okay, and we can take note here that whenever we have a function a raised to n raised to r or something like that, this is the same as multiplying it. So you have a raised to n times r. Okay, and applying that to the denominator we have right here, we actually have secant squared times 5/2 theta. All right, and 2 times 5 is 10, divided by 2 is 5, so we can just cancel these two out, and we are left with secant to the 5th power theta, and we can rewrite that. The integral of secant squared theta over secant to the 5th power theta d theta. Let me just erase this actually there. And now we can just reduce the power. So this cancels, this becomes 3, and this becomes 1, right? Since we're dividing by the power, and when we are dividing exponents, we subtract them. Okay, and now we have the integral of 1 over secant cube theta d theta. And we know that it is the same as cosine cube theta. Let's move on here on this part. It is the same as the integral of cosine cube theta, d theta. And we can break this apart even further. So let's say cosine cube theta, we can take out the cosine squared, right? So we have, let's just do the work here. So we have cosine theta times cosine squared theta. And when we look at this, cosine squared theta is the same as 1 minus sine squared theta. Right? That's pretty good. Since, look over here, we have the integral of cosine theta times 1 minus sine squared theta, d theta. And now we can finally do a nice u substitution here, where we can let our u be equal to sine theta, and the derivative of that is negative cosine, right? No. It's cosine, positive cosine theta, d theta. That's actually referring to other things, okay? Okay? And now we have the integral. Now we are left with this, and we are integrating this in the u world. So we have the integral of 1 minus, our u is sine theta, so we have u squared du. And we can just simply integrate this to be the integral of 1 in the u world is u, and our u is sine theta, minus 1/3 our u is sine theta, and we raise it to another power, sine cube theta. Alright? And now, you may be wondering, is this the final answer? Should we put a plus here? No. Unfortunately, we cannot do that. This is Trig-Sub. Okay? And now, since this is trigonometry, of course we apply trigonometry here. We know that sine theta is equal to the opposite over the hypotenuse. Okay? So, what can we do from here? Okay? Right. So we can draw a right triangle. Okay? We take note of the trig-sub we did earlier. So we know that x is equal to tangent theta. So we know that tangent theta is equal to x over 1. There's automatically going to be an over 1 there. Since we divide by 1, it's going to be x. So we have to use a bit of imagination for that. And this one, we put this here and an angle theta. Okay? And we know that tangent theta is equal to opposite over adjacent. This is the opposite side. This is the adjacent side. And to compute for the hypotenuse, we apply the Pythagorean theorem, in which c is equal to the square root of a squared plus b squared. Okay, so let's do that here. I think we still have some space left to work with. So c is equal to square root of a squared plus b squared, and that is just, let's consider that as x. Yeah, let's consider the opposite sides are x squared plus 1 squared. This is gonna, it will simply be x squared plus 1. Don't forget the square root. So this is our hypotenuse, x squared plus 1. And we can now substitute that for these values right here. Alright? Alright? Okay, here we go. So let's just do this here. So, sine, again, sine is opposite over hypotenuse. So we have 1 over square root of x squared plus 1. Right? That's pretty nice. Now, minus 1/3. Again, no. Opposite side is x. Opposite side is x. Pardon. And you have 1/3 of, again, sine theta is opposite over hypotenuse. This one. I stand corrected. So we have x over square root of x squared plus 1. And then we cube that. Okay? Okay. And then we just distribute this cube here to the denominator and numerator. And then I think we should have a final answer. Okay. Okay. All right. So I think let's erase this part of the integral since we already did that. So I just want to use like one page as much as possible, since I think other problems are gonna take long as well. Okay. You can erase this part right here. Okay. You check. So we can distribute the cube, and let's just do a bit of a turnaround, like right here, right there. So we have x over x squared plus 1 square root minus 1/3 of x cubed over square root of quantity x squared plus 1 cubed. Okay. We can put a plus c now, but we can actually rewrite this again of the form 1/3 of that, but, and we have a square root of a function raised to the third powers is the same as raising it to 3/2, since the square root is 1/2. Okay, so we can actually have x squared plus 1 raised to 3/2 right here, and we can further simplify this by factoring out. Yeah, factoring out x, and then how do you call it? Dividing by the denominator, the 3. Yeah. Since our LCD is this, we can actually put here a plus c, and this is a viable answer, but we can still somehow simplify it, but this will be our answer for now. Then I will further simplify it for another alternative answer. Okay, so this is the same as x times 2x squared, since, yeah, let me explain that later on, plus 3. Okay, so when we have 3x over 3, that's x here, and we have 2x cubed over 3, we have 2/3, which is, yeah, is that right? 2x squared plus 3. Yeah, that's right, that's right. Since we're dividing by the power. Over, right? 3. Square root, no. The LCD right here. X squared plus 1 raised to 3 halves. Okay? Then put a plus C. This is another answer you can put. It's a much simplified version, but both are the same. Right? Okay. Huh. Okay. Okay. Moving on. Number 6. Okay. I think we can do a U-sub here. Yeah. So let's do it. So we let our U be equal to the square root of x. Okay? And then we can actually square both sides. We can square both sides. Okay? And the root will cancel. So that means that u squared is the same as x. It's very good. And when you differentiate that, our dx would be 2u du. Okay? Alright. Yeah. So now we have the integral of e to the u, right? Times 2u du. Now we can perform integration by parts. Okay, so we have the d, and then we have the I, and don't forget the plus minus signs. We will differentiate 2u and we will integrate e to the u. Differentiating, this will become 2, and the derivative of a constant is 0, and then this is just e to the u all throughout. And since this is 0, we will stop, since the other products would automatically be 0, and we will just multiply this to have our answer. So when we multiply this, you should have our answer. Okay? Multiplying. So we have 2u times e to the u. So we just put it there. 2u e to the u. And then the next sign is a minus. 2 times e to the u is 2 e to the u. E to the u. Okay? Then that's actually the answer. Put plus c and substitute back the x value. So we have 2 square root of x times e square root of x minus 2 e square root of x. Let me erase this part. And then we put a plus c. And we are done. Very good. Okay. 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 Moving on. Hmm. Okay. So actually, for this one we have the integral of sine squared x dx, and we can apply an identity here to help us out. And I think it's the half angle identity. Yeah. Rather than the Pythagorean identity, we can rewrite this of the form 1/2 times 1 minus cosine of 2x. Right there. Okay. And we can rewrite this of the form the 1/2, take out the constant, integral of 1 minus cosine of 2x dx. Okay. And then we can do the u sub in our head. So we have 1/2 of x, and then we're gonna distribute this. So we can do the u sub here. We can take out the reciprocal of that and then have the integral of this. The integral of cosine is positive sign, then we apply the minus sign, and then we go from there. So it becomes 1/2 of sine 2x times 1/2, that's 1/4 sine of 2x plus c. Right? Very good. Okay, that's nice. Now, moving on. For number 8, we have the integral of 1 over square root of x plus 1 minus the square root of x. Okay? Now, we know for a fact that u sub will not work. Okay? So we can actually rewrite this. We're just rewriting it, basically. 1 over x, square root of x plus 1 minus square root of x. And what we can actually do is multiply the whole function by 1, namely the conjugate of the function. So its conjugate is square root of x plus 1 plus square root of x over the same thing here, square root of square root of x plus 1 plus square root of x, and then we put just the x here. Okay, so when we multiply this by the conjugate, the square roots here will just be cancelled, and then we retain this here. So we have the integral of the square root of x plus 1 plus the square root of x over x plus 1 minus x. And we can just take this out. And then when we divide this function by 1, it will be the same. So we're actually just integrating x square root of x plus 1 plus square root of x dx. Okay. And now we can do a little u sub here. Okay. So if a letter u be equal to x plus 1, right? And our du would just be simply dx. And then we can just apply this here only on this part. So the integral of u, the integral of u when you apply the square root of something, is the same as raising it to the 1/2 power du plus the integral of x to the 1/2 power dx. Okay, now evaluating this, we shall have, since we're adding 1/2 plus 1, that's 3/2, and then you just simply put the reciprocal of that uh, to the front. Okay, so we actually have two thirds of u, which is x plus 1 raised to 3/2 plus 2/3 of x raised to 3/2 plus c. And then if you want it to be in a one fraction, you can just simply put it out together as the form of 2x plus 1, yeah, 2 times x plus 1, 3/2 plus x raised to 3/2 over 3. And I put a plus c. We're done. Okay, that's pretty nice. That is pretty nice. Okay, all right. I think the next ones are going to be more tedious. Okay. All right. Moving on. For this one, we have the integral of e to the x over secant x dx. So for this one, we can apply integration by parts, but first we have to simplify this. Now, 1 over secant x is the same as cosine x, so we can rewrite this of the form e to the x times cosine x dx. All right. Now we shall do integration by parts. So I put the d and then the I, then your plus minus plus signs. We will be differentiating e to the x, and we will be integrating cosine x. Then we just differentiate this. The integral of cosine x is positive sine x, and the integral of this is negative cosine x. Okay, now since this and this basically repeated, we can stop here, and then we shall have the product of these rather, and the integral of the product of these two functions. That should give us our answer. So actually, yeah, let's do that. Yeah, I think we can fit it here. So we have e to the x sine x minus e to the x. Is it a plus? Yeah, that's a plus, since negative times negative, plus cosine x. Let's just do this at the bottom. Okay, so we have the integral of e to the x cosine x dx is equal to this e to the x sine x plus e to the x cosine x, and then the product of this is a negative integral, right? Negative integral of e to the x cosine x dx. Now what have we noticed? These two are the same. So what we can do is add the integral of e to the x cosine x dx on both sides. So this 2 will simply cancel, and now we're left with 2. The integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. And to remove this 2, we just have to simply multiply everything by 1/2. And when we do that, we are gonna be left with 1/2 e to the x sine x plus 1/2 e to the x cosine x. Then put a plus c. We are done. Okay, that's actually pretty nice over there. Okay, what time is it? It's already 1 a.m. Alright, moving on. Now we are on number 10. Number 10. Okay. Yeah. Again, we're multiplying by the conjugate of the function. So we are multiplying by 1 minus cosine x over 1 minus cosine x. Okay? Alright? So this will be the integral of 1 minus cosine x over 1 minus cosine squared x, dx. And we know that 1 minus cosine squared x is the same as sine squared x. So we can rewrite that of this form: 1 minus cosine x over 1 minus sine squared x. Okay, sine squared x dx. Okay, and now we can what can we do here? No, we're not doing u-sub. We can split this fraction. So we have the integral of 1 over sine squared x, right, minus the integral of cosine x over sine squared x. Okay, and we can split this fraction further, and we know that 1 over sine squared x would simply be cosecant squared x. Okay, and we are actually integrating cosecant squared x dx. And now we can rewrite this further by breaking apart the power minus the integral of 1 over sine x times cosine x over sine x dx. And we know that this is cosecant x and this is cotangent x. Okay, alright, hold on, is that alright? Okay, sorry for that interruption, I just received a call. Okay, so we have the now we have the integral of cosecant squared x dx minus the integral of cosecant x cotangent x, right, dx. And by definition, the integral of cosecant squared x is negative cotangent x, and the integral of cosecant x cotangent x is negative cosecant x. So we'll proceed there, and our final answer would be negative cotangent x plus cosecant x plus c. We're done. Alright, okay, last two, and this won't be simple. Okay, partial fractions for this one. Okay. For this one, we can write this of the form. This denominator we can rewrite as the form of x squared minus 1 times x squared plus 1. And we can simplify this further here, actually. This would be x minus 1 times x plus 1. Okay? And then we retain this, since x squared plus 1 is an irreducible quadratic. Okay? And we will see later on. So now we will have, okay, we will now have the integral of, let's put the ventulum, we have x minus 1 plus x plus 1 plus x squared plus 1 dx. Now we have put an a and then a b, and then since this is an irreducible quadratic, the variable here needs to be linear. So we will have cx plus d. It has to be linear, since this it is a higher degree variable. Okay. All right. So now we can actually simply do the cover up method for a and b. We can do the cover up method for a and b, but for this one we actually have to do the decomposition. So so we can think of this as, okay, let's put it here. Let's put this right here. We can think of this as the integral of x minus 4 over this x minus 1, x plus 1, and then x squared plus 1 dx. Okay, and we can do the cover up method. Now you cover this up and you think what makes it undefined. It would be 1. So we plug in 1 for all of this to compute for a. So we put in 1, 1, 1, and the 1 here. Okay. Now 1 minus 1 is 0. 1 plus 1 is 2. 1 squared is 1 plus 1 is 2. 2 times 2 would be 4. 1 minus 4 is negative 3. So our a would be negative 3 over 4. And for this one, to make this undefined, we simply have to set x to be negative 1 and we cover it up. Okay? All right. See if I'm doing it right. Yeah. Okay. Now, so negative 1 minus 4 is 5. Negative 5. Negative 1 minus negative 1, negative 2. Negative 1 squared. Negative 1 squared is 1 plus 1 is 2. 2 times negative 2 is negative 4. Negative 5 over negative 4, positive 5 over 4. And now to compute for to compute compute for d, we actually have to include this equation now, right here. So this would be kind of the form integral of, it's going to be tedious work right here. Okay, so this is a, we set the whole equation here first. So x minus 4, x minus 1 times x plus 1 times x squared plus 1 dx, which is equal to this right here. Okay, so we have a over x minus 1 plus b over x plus 1 plus cx plus d over x squared plus 1. Okay, okay, let's actually omit the integral sign there first, since we're just doing algebra. Now, to compute for d, we're computing for d first, right? Since if if x is 0, then we can isolate d, since this will c would be 0. So we can compute for d first when we let x to be 0. Let's just put some zeros over here, and then we can actually replace this by the values we got earlier. So that's negative 3, 4, and this is 5, 4. Now we plug in zeros from all over. There's 0 here, a 0 here, and then a 0 here, and then another 0 here. Okay, now let's do this in our head. X minus 4 is negative 4. 0 minus 1, negative 1. 0 plus 1 is positive 1. 0 squared is 1. Plus 1 is positive 1. So negative 1 times positive 1 is negative 1. Negative 1 times positive 1 is again negative 1. So we have negative 4 over 1, negative 1. Okay, which is equal to 0 minus 1 is negative 1. Negative 3/4 divided by negative 1, right? Yeah, is positive 3/4. And then 0 plus 1 is 1. 5/4 divided by 1 is simply 5/4. Okay, alright. And since this is 0, this is 1, so we have plus d, right? Right? And then when you combine this, when you add this together, it will be 8 over 4, in other words 2. So we have positive 4 equals 2 plus d. Okay, and then you can subtract 2 from both sides to compute for d. So we have negative 2 here, we're subtracting it. Okay, so that means that d is equal to 2. Now computing for c, we can actually use any value we want, but we will use the next best value. We used negative 1, we used 1, and then we used 0. So we can let x to be 2 this time. And for this one, let's actually use another method where we can make this as a single line. If you get what I'm talking about, we can erase this. And what you can actually do, hold on. Let me erase that. What we can do is we can multiply both sides by the denominator of the left side right here. right? So let's just multiply everything by this denominator. X plus 1 and then x squared plus 1 right there. Okay, and then this will cancel, and then whatever we can, let's say for this one, this will cancel and this will cancel, and then we are left with this to multiply to that. Yeah, is that pretty clear? Let's write that down. Okay, so we have x minus 4 is equal to a, let's just put it directly, negative 3/4 of x plus 1 times x squared plus 1. Excuse me. Okay, plus, okay, 5/4, and of course this will cancel on this part, this and this will cancel, leaving you with this to multiply, times x minus 1 times x squared plus 1. Okay, okay, and now plus, I think we shall put, yeah, cx, yeah, let's just put a cx there. I'm gonna put it in red. Cx plus 2 plus 2, since that is d, and then we multiply it, we cancel this, and then we multiply but what is left over. Okay, all right, now if we set x to be 2, we can compute for c. Okay, all right, there's gonna be some trouble around here. Okay, so let's do this. You can do the mental math right here, but I want to show the work as well. Okay, so substitute 2, and the 2 here, there's another 2, 2, 2, 2, and the 2. Okay, so 2 minus 4 is negative 2, right? Equal to negative, this is going to be negative 3/4 of 2 plus 1 is 3 times 2 squared plus 1 is 5. 5 times 3 is 15. 15 times 3 is negative 45. 15 times negative 3 is 45. Okay, this is this whole part right here. Plus, this is gonna be 1. 2 times 2 minus 1 is 1. Then 2 squared plus 1 is 5. So that is 5/4 times 5, which is gonna be 25 over 4. Okay, this is this whole part right here, plus 2c. This, since we're multiplying, c times 2 would be 2c, plus, now this, evaluate this side. Okay, so 2 minus 1 is 1, so we have 2 times 3, so that's 6. Yep, that's a 6 right there. And then we can simplify this further. Negative 45 plus 25 over 4 will simply be 20 over 4. 20 over 4, and then you add the work, actually, plus 2c plus 6. Okay, and then negative 20 over 4 is negative 5, and then negative 5 plus 6 would be 1, so we have a 1 here now, right? And we can subtract 1 from both sides, so that 2c would be equal to wait, hold on. This is a parentheses, right? Yeah, this is a parentheses. So that means that when we multiply 2 times 3, which is 6, we also multiply 2c to that, so it will be 6c now. Apologize for that. Since we had 2c plus 2 earlier, that is a quantity, we multiply that by 3, that will become 6c plus 6. Okay, hope that clears some things up. So 6c is, this is negative 3 now, since we took out the 1 from this side and added it to the other side. Let's put the 6c here. Now we can divide both sides by 6, and then this will cancel, and that means that c is equal to negative 1/2, right? Okay, and that is for c. And remind you, we're not integrating yet. That's negative 1/2. And I think we can finally integrate now. No? Yeah. Huh. Yeah. Can I fit this here? I can probably. But I just won't bother, just make a new frame. Okay. So now what we have is, let us write it properly. So we have the integral of negative 3/4 of x minus 1 dx plus, actually let me move in a little closer, plus the integral of 5 over 4, actually no, let's make it as one integral, since we're all integrating x anyway, plus 5 over 4 x plus 1 plus negative 1/2 of x plus 2 over x squared plus 1 dx. And we can factor out negative 1/2 from here. So this will be negative 1/2 of x minus 4. Yeah, so this will be positive 2. Okay, I think that's right. Okay, and now we can actually answer this part already. That will be an ln function. If we integrate it, we can do the u-sub in our head. So for this segment right here, we shall have we shall have negative 3/4 times the ln of the absolute value x minus 1. That's the part of there, plus 5 over 4 natural log of x plus 1, natural log absolute value, plus, now we can take out the constant negative 1/2 and then split apart split apart this into different integrals. So let's just put the minus here. Minus 1/2. Now let's put the parentheses. Now we have the integral of x, x over x squared plus 1 dx minus, this is going to be a 4, we just take that out, 4 integral of 1 over x squared plus 1 dx. And for this one, you can just do du sub in our head, since this will be 2x, then we divide, we let u to be x squared plus 1, so we have 2x, so 1/2 du is x dx, which is right there, right here, and then it becomes an ln function, and then we can distribute this to find it out. Okay, so we can do that. For this one, this is an inverse tangent situation, arctan, so to speak. So let's do the work here actually. So we can find out the answer for this. This is actually the answer. We can just write this down and then evaluate the answer from here. Okay, so we have negative 3 over 4 absolute value x minus 1 plus 5 over 4 ln of absolute value x plus 1. Now this is just this right here would be 1/2 ln of x squared plus 1. Am I right? Yeah. And then we can just distribute the 1/2. It will be 1 over 4 ln of x squared plus 1. So you're wondering why I didn't put the absolute value. So it means that this equation will always be positive, since even if we square a negative number, it will be positive. Minus 4. This is an arctan situation, so we have 1 over a. Okay, so that's 1 over a is 1, so that's arctan of right. Actually, yeah, we still have a 1/2 here. Yeah. Still have a 1/2 in the parentheses. Yeah, so distribute that here. This negative 1/2 will go here as well to the negative 4, so that becomes positive 2 plus 2, and then our u would just be an x, right? Our tangent of x. Yeah, since if we extract the root, that will just be, that will be our a, u over a, and that is 1, x over 1 is x, then we put a plus c. We're done. All right, that's pretty hard, huh? Okay. All right, I'm getting hot in the suit as well. So let's wrap this up quickly. So for our final example, we have the integral of x squared over the square root of 1 minus x squared dx. So we can't do u sub yet. So we can do a Trig-Sub, since you notice that this is of the form arcsine, right? Okay, so that means we can let our x be we can let our x be sine theta, and our theta would be later on, that will just be an arcsine. We can show the work later on. We're just setting parameters. Okay, and dx would, of course, that would be cosine theta d theta, cosine theta d theta, right? So let's go up here. Now we have the integral of x is sine theta, so we have sine squared theta over the square root of 1 minus sine squared theta. Then we have cosine theta d theta. Is that right? Yeah. Yeah. Mm-hmm. Mm-hmm. All right. All right. Okay. So 1 over sine theta is the same as cosine squared theta. So we have sine squared theta over the square root of cosine squared theta. And let's make sure that we have the cosine theta here, d theta. Now, we can cancel cosine, right? And then the root cancels as well. We can cancel the root first. Yeah, and we're left with cosine theta, and cosine theta is right there as well, so we cancel this as well. So we're actually just integrating sine squared theta, right? And you know, this is number 7 from earlier. And let's just show you the work for the sake of doing the work. So this is the same as the 1/2 of the integral of 1 minus cosine of 2 theta d theta. Again, this will just be equal to, let's go up here. Okay. Okay, so 1/2 of so we have theta, 1/2 of theta, since integrating 1 in the theta world gives us theta, minus the integral of this is yeah, I think we can do something about this. Yeah. So this is 1/4, and this 1/4, since that becomes negative, you can refer to the solution in number 7 from earlier. It's 1/4 sine of 2 theta. Okay, and now we know that theta is arcsine, so 1/2 theta is arcsine. Okay, so that we put arcsine, right, minus 1/4 sine 2 theta is the same as 2 sine theta cosine theta, double angle identity. 2 sine theta cosine of theta, right? And I think, do we actually need to put a right triangle? Actually, let's just do it. Let's put a right triangle here, just for the sake of it. When you have an angle theta right here, So we know that sine theta is equal to x over 1. Okay, sine theta is equal to x over 1, opposite over the hypotenuse. Okay, and then that to compute for b, we just use the Pythagorean theorem, which states that to compute for b, it is equal to the square root of c squared minus a squared. So this is just c squared 1 minus a squared x squared. And you see where the arc sign comes from? Yeah, this is that. Okay, so okay, now we just evaluate sine of arc sine, right? Okay, let's just do this here. Okay, we'll write the final answer here, but we will evaluate this right over here. So sine of inverse sine, let's just put it inverse sine, this would be equal to what? Right, since sine is opposite over the hypotenuse, and sine arc sine, we do that. But that would just be equal to x, right? Yeah, that would be x right here, right? Yeah, and then cosine of arc sine, that would be the adjacent side, right? Yeah, that would be the adjacent side. That is 1 minus x squared. Yeah, I think so. Yeah, because I think there's some definition here that the inverse sine is just the hypotenuse over the opposite side, right? Since x over 1 and then the 1 over x. No. We're just doing it for the sake of the integral, so I think we can leave this as that. We can figure that out. I also made some mistakes here throughout the video. Please forgive me. It's like, what time is it? It's almost 1. It's almost 2 a.m. in the morning. All right. So we have yes. So this will get reduced to 1/2. We can cancel this out. So we have 1/2 of x times square root of 1 minus x squared. I think I can do a better explanation of this in the future when I understand it further. But this is the final answer. Put plus c. We're done. Alright. And I think that does it for this video. Let's just go along and let's see if I made some few mistakes along the way here and there. So yeah, so that does it for this video. I hope you have learned about some concepts of the basic integration techniques that we're going to utilize in the later weeks in the semester. So that's it. If you like this video, consider giving a like. And yeah, I think that does it. It's 1:50 a.m. and I am going to sleep. Okay, good night and thank you. Bye bye.